Hi, I'm Ben-Yaakov. This presentation is entitled A Simple Simulation Model of a Rechargeable Battery. Now, there are many models of batteries that one can use. There are some very sophisticated one, but many a times one needs a very simple and straightforward model that one can sort of put together very quickly in order to test charging, discharging, maybe equalization. And this is the objective of this presentation, to show a very simple model that you can build up very quickly. Now, we know that when you discharge a battery, typically you'll get lines like this. This is for a lithium-ion battery, and this is for different discharge current. Now, 1C is the number in amp hours capacity, so say a battery of 10 amp hour, then 0.2C will be 2 amp. So this is 0.2, 0.5, 1, and 2C. And obviously, the heavier the discharge, then there is a drop. This is the voltage of the battery, and this is the state of charge or capacity, in this case in milliamp hours. So this battery, by the way, is 2 amp hour. Now, this is then the discharge behavior. On the other hand, when we charge a battery, we have a similar curve, depending on the battery, the chemistry, etc. And as we can notice, there is a sort of a hysteresis between the charging and discharging. That is, the voltage during charging for a given state of charge will be higher than that for discharging. This kind of suggests that you can perhaps model it by a series resistor or two series resistors, one for charging and one for discharging, for this voltage drop, and we'll see it in a minute. Now, obviously, in between the charging curve and the discharging curve, we have the open circuit, and I'm assuming a long rest time so that the battery is stabilized. And so the open circuit will be somewhere here in between. And so there is a difference to charge curve and a difference to the discharge curve. So here is the basic model and the idea behind it. We start off with a capacitor which accumulates the current of the battery. This is representing the battery. This is a voltage dependent source. So we measure the current, duplicate it here, and feed it to the capacitor, which sort of integrate the current, so we get here a charge as a function of time. Now this dependent source, this voltage dependent source, now represent the battery. Given the charge, you have a certain voltage. That is, here we have the dependence between the charge, the state of charge, you might say, and the voltage of the battery. This is this open circuit curve, the rest voltage. Now, we can make a voltage dependent source that will behave like this, and we'll see it in a while. And then we have here two resistors, one for the voltage drop during charging. So the voltage, this is the terminal of the battery, the terminal. So the voltage here will be higher than the inherent battery voltage during charging. And then we have a discharge resistor, so that the voltage here will be lower than the inherent battery voltage. So from this curve, I can estimate for the given current, I can estimate the resistor here. I did it in a very sort of a simple way, intuitive way, just assumed values, and I didn't actually calibrate the model I'm going to show very accurately or very precisely or very carefully. It is just a way of showing the idea, and obviously if you have the charge and discharge for different current, then you can do a much better calibration of the model. And here is the model. This is in PSpice. And we start off with the capacitor. This is the capacitor which is being charged and accumulating the charges. Now this is a dependent current source which duplicates the current that goes into the battery. This is the battery, this is the dependent source, dependent voltage source. We duplicate it by having here a voltage source of 0 voltage. This is a way in SPICE in general to measure. This is like a current sensor. So we can refer to the current in the battery by writing here I of V2. I of V2 is the current going into the positive terminal. This is a classical way of doing it in SPICE. So we have a current source duplicating the current into the battery, accumulating the charge, and now this is an E-table. This is a dependent source that this actually represents the x-axis, that is the horizontal of the graph. Now then we have a table, and here is the table, which is a digitized form of this curve. That is, it has the points of x, y, xy, xy, etc. Okay, I did it just eyeballing it, and I here have it here. This is the table. So this will be the charge, voltage, etc. up to 95. I'm assuming here that the maximum capacity is 100, just a number. Now, aside from the basic blocks, which is the capacitor, current source, voltage source, and the resistors, I have also some clamping diodes. First of all, I'm clamping here the charge to 100, so I can't go above it. I'm clamping the charge to the positive, so I can't go negative charges. And also, I've clamped the voltage here, the inherent voltage of the battery, to a given value. In this particular case, just chose it to be 4.3. So it will clamp here, and also the charge will clamp here. And then we have the two diodes, which are sort of estimated. Now, just took these two values for the example I'm showing. Now, in order to get rid of the diode voltage drops, I have many diodes here, I've actually modified the diode. You can do this by sort of right-clicking an element like a diode and then choosing Edit SPICE Model, and then you'll have this window coming up. This is editing the model of an element in SPICE or PSpice, and this is a diode model. Now, the diode has many parameters. They are not shown here, not all of them. If they are not shown here, then they are the default value. And I'm in particular interested in N. This is the emission coefficient. This is the diode equation. This is the emission coefficient. The default value, by the way, is 1, and it's not written here. I've written this N equal to 0.01. Now, the smaller the N, the faster the current will shoot up, because if this is a small number, then for small VDs, you go up very quickly. So by making this N to be 0.01, I can make a diode which is almost an ideal diode. And in order to verify it, I've actually built here a auxiliary circuit here, which is just sweeping this voltage source, measuring the current to see the characteristic of the diode. And here it is. You can see that this diode is indeed almost ideal at 0 volts, so it shoots up with almost, well, within this resolution we can see the voltage goes up to 10 amp already. So this is like a ideal diode. So now I'm going to see how this model behaves. So first of all, I'm feeding in a current and looking at the charge, and at this point I'm calling it pulse. This is actually the battery terminals. This is the inherent battery, and this is plus or minus the voltage drop on the resistors. And here it is. We see the charging. This is the charge accumulating here, and this is the state of charge, you might say. Here is the voltage. This is the curve that I've sort of approximated, and here it is clamping to the values that I've decided on. This is the voltage here, and this is the almost 100 charge. So this is the charging, and you can see that this curve is pretty much close to this one. Well, again, it was done sort of quickly, not very accurately, just for the purpose of giving an example. Now, I can then use different current to charge the battery, and here we see it. This is the lower current, the higher and higher. Of course, with the high current, you very quickly reach the clamping voltage, and of course the charge will come up to the maximum more quickly. So you can see here the behavior of charging and discharging, and you see that the current is actually changing the battery voltage during charging, because, and this is realistic, well, it's not accurate because it's not very well calibrated, but it is realistic because the higher the current, the higher is the voltage increase during charging. And then you can reverse the current, and of course see the discharge. I didn't say that for the charging I've taken an initial condition here of 6, just arbitrarily. So we start with a state of charge of 6 going to 100, and in this case I've started from in the discharge from 100 Q of, this is Q, 100, and then I'm discharging, and you can see very nicely also for different current how this circuit behaves. Now, I can then use here a sort of a pulse. This is a pulse source, voltage source, which is has a certain period and pulse width, and I'm then charging and discharging the battery with this thing. This is a current source feeding into the terminals of the battery. Let's have a look now at the sequence. This is the current. I'm charging here. Here the charge goes up to maximum. Stop charging because it's already fully charged, and because the current is actually bypassed to the clamping circuitry. And then at this point I'm discharging with this current at 30 amp, and so the charge goes down, and also the battery voltage goes down, and then it goes up and down, up and down. Now I can do something nice here. I can change this scale, which is now time, into state of charge. That is to change this scale into V of Q, that is the accumulated charge. You do it by clicking this scale here and then changing it, changing the axis to this. And here it is. This is now state of charge. We go from 0 to 100. This is the inherent battery voltage. This is this one here, which has been approximated by this curve. And here we see the terminal voltages, and we see very nicely the hysteresis. This is during charge, and this is during discharge because of the resistors that we have. And this is, of course, very similar to what we have here. Again, it is not very calibrated, etc. But again, we can see just the idea of this very simple and very easy to construct model. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it interesting, and perhaps it will be useful to you in the future. Thank you very much.